Welcome back, and in this short series of videos we're going to be looking at ionic bonding. That's the electrostatic attraction between oppositely charged ions based on their size and their charge. So you're going to need your notes, and we're going to start on page 1. So as we said, an ionic bond is an electrostatic attraction, that just means positive attracting negative and vice versa, between oppositely charged ions. They're usually formed by electron transfer from a metal to a non-metal, but the actual definition you need is just this part, electrostatic attraction between oppositely charged ions. So the group which has the greatest tendency to lose their outer shell electrons, you should know this from GCSE, is group 1. The reason for that is that they have the lowest first ionization energy of their period. The next most likely is group 2. You need to be careful in your explanations. At GCSE you probably would have been allowed to get away with ideas of it wanting or needing a full outer shell. At A level we have to explain things in terms of ionization energies. So we need to talk about why the first ionization energy is relatively low. And the same with the group 2, and the energy that is then released by forming the ionic bond compensates us for the ionization energies. In fact, in group 2 there's an element which doesn't form ionic bonds very easily, and that's beryllium. Now you can argue it that beryllium, because it's so small and it has a high proton number and very little shielding, the energy required to form the ion is not compensated for by forming the ionic lattice. The other way you can talk about it is what we call polarization, where the beryllium ion has a high charge density and can polarize things very effectively, again leading to a covalent rather than an ionic bond. And again, which group of elements has a tendency to gain outer shell electrons? Well, that would be group 7, the halogens, and the second most likely is group 6. And again, we need to be careful that we're not explaining this in terms of wants and needs, full outer shells. They do become isoelectronic with a noble gas, and that is a stable electron configuration, but in terms of our explanation we need to be talking about the fact that they find it most easy to gain an outer shell electron. We call this electron affinity, the ability to gain an electron. So for example, the first electron affinity of oxygen is very similar to ionization energy, except this time we are gaining an electron to become an O minus, and then we take our O minus and we add another electron to become our standard O2 minus. This one actually releases energy. It's one of the unusual. It's actually exothermic, kilojoules per mole. This one is endothermic because we're trying to add an electron to an already negatively charged ion, and that's plus 798 kilojoules per mole. But by forming these 2 minus ions we can then form a lattice, and that's going to release a lot of energy, and it's going to release a lot more energy than is required to add the electrons. So it comes back again to this idea of energy compensation, and we'll study this more in thermodynamics. So this time the energy change to add an electron is compensated by forming the lattice. We can also talk about the fact that they are now isoelectronic with a noble gas charge. So we're just going to practice some dot cross diagrams on the next page, and in these dot cross diagrams we usually only show the outer shell electrons, and also we only show principal quantum shells. We don't show subshells or orbitals in these diagrams. So the sodium atom has 1 electron in its outer shell, and it has the electron configuration 1s2, 2s, 2s2, 2p6, 3s1. The chlorine atom, on the other hand, has 7 electrons in its outer principal quantum shell, so that would be 1s2, 2s2, 2p6, 3s2, 3p5. The ion, on the other hand, sodium will lose its outer shell electron to become Na positive, and again I've got 1s2, 2s2, 2p6, no 3s now because that's empty. You can draw 8 electrons in this outer shell because we've now gone 1 shell in. The chloride ion, on the other hand, has become negatively charged, and by convention we show that extra electron as a dot rather than a cross. We don't actually need to because obviously all the electrons are the same. Again, electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. And these now have the same electron configuration, in other words they are isoelectronic with the noble gases neon and argon. And we can do the rest of them on that page and the next page. So here we have magnesium, and I've drawn both all the shells and the outer principal quantum shells. Again, when it becomes a 2+ ion, it loses those outer shell electrons. And here the oxygen is gaining 2 electrons. So on the next page we're looking at sodium oxide. Now there need to be 2 sodium ions for every 1 oxide ion. So the easiest way to do that is put a big 2 in front of it, and quite often you'll see it with brackets around to show that you've got 2 separate ions. And the same for the chlorine. Brackets around to show I've got 2 of those, and I've got 2 chloride ions, and sometimes you'll actually see the charge on the outsides of the brackets. Do you remember there's nothing special or magical about noble gas configurations? There are lots of examples where ions do not have a complete outer shell. Most of the transition metals don't do this, and also you've got to remember we've also got complex polyatomic ions that you need to have learnt. So looking at these ionic lattices, we need to understand that we have ionic bonding, but we also have a particular type of structure. So ionic bonding is that electrostatic attraction between the oppositely charged ions. So the bonding is ionic. The structure, on the other hand, is what we call giant ionic lattice. In other words, it's a regular arrangement of oppositely charged ions. In this diagram here, I have these ions, and they are oppositely charged, and they form this large lattice. And this is an example of a sodium chloride crystal. Now the ratio of sodium ions to chloride ions in this will be 1 to 1. So the formula of sodium chloride is NaCl. 1 Na for every 1 Cl. But unlike a molecular formula, it doesn't tell us the actual number of species present in my compound, because you can see from the diagram I've got far more than 1 sodium and 1 chloride. So with the ionic structures, it only gives us the ratio of the different species. When you come to draw these, do make sure you give a key so I know what sort of little blobs and big blobs mean. As a general rule of thumb, the smaller blobs are your positively charged ions because they've lost electrons, and your larger blobs are your negatively charged ions because they've gained electrons. So I have Na positive, Cl negative. So if you actually look at one of your chloride ions, you will see here it has 6 sodium ions surrounding it. 1 up, 1 down, left, right, forwards and back. And if you do the same for the sodium ions, you will also see that it has 6 chloride ions. Up, down, left, right, forwards, backwards. And that's why it's called a 6-6 coordinate number. because each chloride has 6 sodiums around it, and each sodium has 6 chlorides around it. So the space filling model on the front is a better representation, but it's a lot more difficult to draw, which is why we often see the expanded diagram that we saw on this page. Now, this is absolutely key, so you do need to start this. This is very important. Okay, not only is this talking about the coordinate numbers, but also the strength of the ionic bonding. So the strength and the coordinate number depend on 2 key factors. They depend on the charge and the size. So it's charge and size that determine the strength of the ionic lattice. So the charge of the ions and the size of the ions. And that's a very important principle in chemistry. And in fact, that holds true for all different types of bonding, not only ionic, but also covalent, that it's the charge and the size that determine the strength. So if you look at the back of your coloured periodic table, which you were given in class, you can compare the size of the atoms and the cations that they form. And you have to understand that cations are smaller than their parent atom. The reason for this is they've lost electrons, and that may result in them losing the total outer shell of electrons. You've now also got more protons than you've got electrons. So those electrons are going to be pulled in tighter towards the nucleus. You could also, if you've lost an outer shell of electrons, also have lost a level of shielding. All of these impact on the size of the cation, making them smaller than their parent atom. Anions, on the other hand, are larger than their parent atom. You've gained electrons, so you've got greater electron repulsion, so they're held less strongly. As you go down the group, you've got more protons, which would force it the other direction, would make it smaller. But you've got 2 competing factors. You've got more shielding, which is provided by complete inner shell of electrons, and you've got another complete inner shell, so your outer electrons are further away from the nucleus. So whether you're a cation or an anion, they increase in radius as you go down the group. And you can see that again on your coloured periodic tables. So on the next page, we need to look at isoelectronic ions as we go across a period. So if you start from neon, if you like, and you go forwards, all of these ions have the same electron configuration as neon. Sodium has lost an electron to go back 1, magnesium has lost 2 electrons to go back 2, and aluminium has lost 3, going back 3. Likewise, fluorine has gained an electron to become fluoride and gone forward 1. So all of these ions have the same number and the same arrangement of electrons. But as you can see from their ionic radius, they are decreasing. And that's because nitrogen here has gained a large number of electrons. It's still only got 7 protons in its nucleus. Whereas aluminium has lost 3 electrons, it's lost its total outer shell of electrons, and it's got 13 protons in its nucleus. So it's going to be a much smaller ion. You do need to know this order. So this strength of the ionic bond is very important, and as we've said, it depends on 2 things, the charge and the radius, or the size of the ions involved. And that determines the strength. So I can look at the charge and I can look at the radii, and I can determine whether one ionic bond is going to be stronger than another. So for example, in the dot cross diagrams we did, magnesium oxide was the strongest ionic lattice. It had the strongest bonds. And that was because it had a higher charge and a smaller radius. Now the physical properties that this strength of ionic bonding will determine is the melting and boiling points. So the stronger the electrostatic attraction, the higher the melting point, because you need to put in more energy to overcome that strong electrostatic attraction. We're going to be studying that in the next video.